Assalamualaikum and hi, see you again. This week we will learn chapter 8, topic differential equations. We shall cover subtopic 8.1, introduction to differential equations, subtopic 8.2, separable variables and integrating factors. The learning outcomes for subtopic 8.1 are to define the differential equation and then to understand the degree, order and solution. Okay, we look at the definition of differential equation. A differential equation is an equation that contains a variable x and y with at least one derivative of y with respect to x, means dy over dx. Example of differential equation: for the first order, dy over dx equal to 4x. This is the first order. And then the b, the derivative also 1 here, dy. So this is first order, dy over dx. This is the degree, plus y square plus hyperbolic sign x. This is the example for second order differential equation, xy double prime. Okay, means x d over dx square, dx square, yes, plus dy over dx. Okay, the second order. This one also the second order. Okay, this is the first order derivative. So means the highest derivative is power of 2, means this is the second order differential equation. For E, the third order, means here the highest derivative. Okay, we have power of 3 and power of 1 of the derivative. Okay, means that this is the third order of differential equation. Order of a differential equation is given by the highest derivative in the equation. How about the degree of differential equation? Degree of a differential equation is given by the degree of the highest derivative. Degree of the highest derivative in the equation. The means that the highest power of highest derivative. For example, here dy over dx square equal to 4x, means that this is the first derivative, right? The first derivative, and then the degree is power of 2. B, the first degree differential equation y, because the highest derivative is here, the second order. Okay, the second order, but the degree is power of 1. Okay, that one it is first derivative. Even here the power of 3, but the derivative is 1. This one, the derivative is 2. Okay, so this is the first degree. C, what is the highest derivative of this equation? Third order derivative, right? So means that it has the second degree of differential equation. For exercise, means here ds over dt equal to 40. This is the first order dE, and then the first degree. Okay, power of 1. And then this one, the first order, okay, the first derivative, but second degree. This one, the second order, because here the second order derivative, the highest derivative is the degree is a power of 1. This one, the second order derivative, and then the third degree. For situation 1, we look here, dy over dx equal to x, and then we integrate dy and then bring up here for dx. Integrate dy, we will get y, and then integrate 2x, we will get 2x squared over 2, can cancel out, plus c. This is the general solution, which is we don't know yet the value of constant. In situation 2, given dy over dx just now, and then we given the value of x and y. Just now we get x squared plus c. Alright, and then now we substitute the value of x into the equation. We will get c equal to 1. Therefore, y equal to x squared plus 1. So means that this is the particular solution. The general solution of a differential equation contains the constant c. For the particular solution of a differential equation contains a specified initial value and containing no constant. The learning outcomes for subtopic 2 are to define separable differential equations and then to solve separable differential equations. Okay, look at here. A first order differential equation whose variables x and y are separable, separable, is of the general form gy dy over dx, here y and then this also y, equal to fx. Consider the first order differential equation like equation number 1, y dy over dx equal to 3x squared. Okay, by integrating the both sides of equation 1 with respect to x, okay, x here, so we integrate y dy over dx with respect to x equal to integrate of 3x squared dx. So here can cancel out, so integrate y dy equal to 3x squared dx. This equation 2, also can be obtained if equation 2 is written by taking the x to the right hand side. Means that here we just going up to the right hand side. So integrate y dy equal to integrate 3x squared dx. Hence we have here, we integrate y, we will get 1 over 2y squared equal to 3x cubed plus c squared. Because integrate 3x squared, we will get x cubed plus c. In example 1, solve the differential equation x dy over dx equal to y by separating the variables x and y. Okay, we can obtain here for left hand side it would be y, and then the right hand side would be x. So bring to the y to the left hand side, we will get 1 over y dy equal to this x. Bring to the right hand side, we will get 2 over x, because this is the multiplication. Bring to the right hand side will be division, 2 over x dx. And then by integrating the both side, left hand side and the right hand side, we will get this equation. Okay, integrate both sides. Integrate 1 over y is ln y. Integrate 2 over x, we will get 2 ln x plus c, which is c is a constant. The multiplication here means that ln x squared plus ln a, which is ln a equal to c, and then ln y equal to ln a x squared, since it is plus here. For ln it will be multiply ln a x squared. So left hand side and then right hand side we cancel out, so we get y equal to a x squared. y equal to x squared is a general solution of the differential equation, and it represents a family of curves where each value of the constant a gives a particular member of this family of curve. For example, when a equal to 1, a equal to 2, and a equal to 0.5, we have three particular members of this family for the curve y equal to ax squared, like this one. When y equal to 0.5 x squared, this one when y equal to x squared, the blue color is when y equal to 2x squared. In exercise 1, we need to solve the differential equation. Okay, you can solve this one. Still remember to separate the variable y must be left hand side and x must be the right hand side, right? So we have this 1 over x dy over dx equal to 2y over x squared plus 1. So we need to separate. Separate means we get 1 over y dy, integrate 2x over x squared plus 1 dx. Okay, integrate both sides. Integrate 1 over y, we will get ln y, and then integrate this one, we can use a substitution method, right? Which is here we can let u equal to x squared plus 1, and then differentiate du over dx, we will get 2x, means du is 2x dx. Okay, so now you can substitute the 2x dx is equal to du. So x squared plus 1 is u, right? So we can say here 1 over u du. Okay, this is just now the du is 2x dx, and then x squared plus 1 is u. Okay, now we can ln y, integrate 1 over u, it will get ln x squared plus 1 plus c, since u is x squared plus 1. Okay, we know that c is ln a. Okay, so y equal to a times x squared plus 1. You still remember just now, which is c here is the ln a, means that ln y ln x squared plus 1 plus ln a, right? So this is a plus here, means for ln it will be multiply. So can cancel out left hand side and right hand side. We can get y a x squared plus 1, the general form. Okay, it also can be like this. This is the but it's not the final answer. This is the general form. Okay, y equal to ax squared plus 1. And then the example 3, find the particular solution of the differential equation. Okay, given this equation, ex plus 2y dy over dx equal to ey minus 2x. Okay, this is for exponent. This plus here will be multiplication. Ex times e2y dy over dx equal to ey exponential negative 2x. Then exponential 2y over y, we separate the variable. Okay, left hand side y, the right hand side x. Okay, exponential 2y over exponential y, and then exponential negative 2x, bring here will be division. over exponential x, and then this one exponential 2y minus y. For division, it will get ey dy over dx exponential negative 2x minus x. It will be negative 3x, and then we need to integrate both sides, left hand side and the right hand side. Integrate exponential y will be exponential y. Integrate this one exponential, we will get itself exponential negative 3x times negative 1 over 3 plus c. Okay, when x equal to 0 and y equal to 0, we substitute into this equation. We will get c equal to 4 over 3. Okay, we can substitute here the value of c, and then to neutralize the exponential, we multiply with ln left hand side, and the right hand side we multiply with ln. So ln exponential, we get y, and then ln 4 over 3 minus 1 over 3 exponential negative 3x. Okay, we continue to subtopic 8.3, the general rates of increase. We know that a derivative is all about the change, okay, which show how fast something is changing. We call as the rate of change at any point. So means the rate of increase dy over dx represent the rate which y increase compared to x. So when the variation in one quantity p depends on the changing value, okay, the rate of change of the another quantity of q, then the rate of increase of p compared with q can be expressed as dp over dq. The situations where the such relation exists, for example, the liquid expands when it is heated. When V is the volume of a quantity of liquid and T is the temperature, then the rate at which the volume increase with temperature can be written as dV over dt. The profit P made by a company selling cars depends upon the number of N of cars. So you can say that dP over dN can represent the rate of increase of profit compared with sales. Differential equations often come from a physical situation when it is modeled mathematically. A body fall from rest in a medium that causes the velocity to decrease at rate proportional to the velocity. The velocity is decreasing with time, so its rate of increase is negative. Okay, negative. Using v for velocity and t for time, the rate of change of velocity can be written as negative dv over dt, because here the velocity is decreasing with time. Okay, negative dv over dt proportional to velocity. Then the motion of the body satisfies the differential equation like negative dv over dt equal to kv, which is k is the constant. Differential equations often come from a physical situation when it is so just same like the previous slide. Okay, this one it is a decreasing, right? Okay, but this one differential equations often come from a physical situation when it is modeled mathematically when yeast cells grow. Just now it is decreasing, it will be negative. If it is grow in a culture, the number of cells increases in proportion to the number already formed. So n the number of cells at a particular time t such that dn over dt proportional to n. Okay, the number of cells can be found from the differential equation dn over dt equal to kn. It is grow, it will be positive value. When it is decrease, it will be negative value. For example 1, here, represent the differential equations, the given data. A body moves with velocity which is inversely proportional to its displacement as, okay, the distance from a fixed point. Means that ds over dt, the displacement, okay, over dt equal to proportional, right? So k times 1 inverse proportional, k times 1 over s, right? Because it is inversely, so we can get k over s. We know that the velocity, okay, the rate of change of the displacement, okay, that's why we get here ds over dt, the rate of change of distance or displacement. So ds over dt, we know that v equal to ds over dt. Okay, if you want to get back the value the s, okay, as the displacement, we need to integrate the velocity. Alright, solving 8.5, solving natural occurring differential equation. Naturally occurring differential equations often involve a constant of proportion. The initial solution will involve this constant and a constant of integration. Therefore, two pieces of information are needed to find the values of these constants. Okay, the example 1. A particle moves in a straight line with an acceleration that is inversely proportional to its velocity. Acceleration is the rate of increase of velocity. You need to form a differential equation to represent this data. Using dv over dt for acceleration give dv over dt proportional to inverse velocity, okay, inversely. So dv over dt equal to kv. Remember just now dv over dt, k times inversely proportional to velocity. Okay, b, given that the acceleration is 2 ms power of negative 1 when the velocity is 5 ms negative 1, find a new differential equation. Wait, I think acceleration ms power of negative 2, right? Because the velocity ms power of negative 1, so the rate of increase of the velocity based on the acceleration based on the velocity, so it should be ms negative power of negative 2. Okay, for v equal to 5 when dv over dt equal to 2, so 2 equal to k over 5, which is k equal to 10. Okay, we know that the velocity is the rate of change of the acceleration, is the rate of change of the velocity. So when the velocity is 5, okay, here dv over dt equal to 2, substitute into this equation, we can get k over 5. So k, the constant k is k equal to 10. Means that dv over dt equal to 10 over v. Okay, substitute into this equation. In example 2, the rate of decay of a radioactive substance varies with the mass of the substance remaining. Write a differential equation that represents this relationship. If the mass of the substance remaining after 12 years is half of the original mass, what is the percentage of the substance remaining after 6 years? Okay, we let that mass mt equal to the mass of the radioactive at time t. We know the mass, okay, here means that dm over dt over time, the rate of change of mass over time, equal to negative km. Why negative? Because it is decay, okay, the disintegrating, which is it will reduce the number of atoms, okay, that's why here we will get negative. And then we separate the variable, okay, left hand side is m, the right hand side is k, so bring to left hand side the value of m. We will get the variable integrate 1 over m dm equal to negative integrate of k dt. Okay, integrate 1 over m, we will get ln m, and then integrate negative k, we will get negative kt plus c. To neutralize the ln m, we multiply exponential with both hand side. Okay, ln m exponential m, and then we will get exponential negative kt plus c. And then we know here the plus means negative kt times exponential c. So we can let exponential c is a, therefore m equal to a exponential negative kt. We let m naught is the original mass of the radioactive, and t equal to 0, okay, the original mass means that mt equal to m naught. Okay, we know that just now m is this one, okay, the general form. The m naught equal to, we substitute the value of t equal to 0, and then a equal to m naught, therefore, okay, this one, a equal to m naught, therefore m equal to m naught exponential negative k t. Okay, now just now we write the differential equation, and then we answer if the mass of the substance remaining after 12 years is half of original mass. So when t equal to 12, mt equal to 1 over 2 of the original mass. Okay, when t equal to 0. So we know that just now m, okay, m equal to m naught exponential negative kt. Okay, m equal to m naught exponential negative kt. So m is 1 over 2 of m naught. So we substitute. Okay, we can cancel this one. So exponential negative 12k equal to 1 over 2. Okay, we multiply with ln right hand side and the left hand side. Okay, and we get negative 12k equal to negative ln 2. Okay, this one it is negative ln 2. Then we solve this one, we will get k equal to this. Therefore, we can say that from this formula, okay, we substitute 0.05776, and then when t equal to 6, the question asks what is the percentage of the substance remaining after 6 years. So when t equal to 6, we substitute into this equation. Okay, m equal to half of m naught exponential 0.05776, and then we substitute the t value is 6, then we get 0.7071 m naught. Then the percentage, okay, 0.7071 m naught after 6 years over the original when t equal to 0 times 100%, we'll get 70.7%. Okay, we look at the exercise 1. The rate at which the atoms in a mass of radioactive material are disintegrating. Okay, disintegrating is means equal to decay, is proportional to n. The number of atoms present at any time. Initially, the number of atoms is m. Equation A. Form and solve the differential equation that represent this information. Okay, the rate at which the atoms are disintegrating is negative because it reduces the number of atoms n. So that's why the sign is negative. So negative dn over dt equal to km means that multiply with negative both sides, we will get negative km. Okay, integrate both side, which is we separate the variable. N is left hand side, then k right hand side. So integrate 1 over n, we can get ln n. Integrate k, we'll get negative kt plus c. Okay, so c here we let as ln b. Okay, ln n over ln b, bring to the left hand side. Okay, ln n minus ln b equal to negative kt. So that's why here we get ln n over b equal to negative kt. So here we multiply both sides with exponential. So n, this is bring to the right hand side, n equal to b exponential negative kt, which is when t equal to 0, n equal to m. And then which is b equal to m. Okay, because initially the number of atom is m. So initially to means that when t equal to 0. So here when t equal to 0, n is m. Okay, which is n is the number of atoms. So therefore here b equal to m, and then therefore n equal to m exponential negative kt. The rate at which the atoms in a mass of radioactive material are disintegrating is proportional to n. The number of atoms present at any time initially. Okay, just now we have this. Okay, we can solve this one. And then for B, given that half of the original mass disintegrate in 150 days, evaluate the constant of proportion in the differential equation. So when n is half of the original is m. Okay, so half of m, then t is 152. We have just now n equal to m exponential negative kt, right? M is the original at origin, okay, initially when t equal to 0, and n is half. Okay, for B equation, the equation B asks when n is half of m, so 1 over 2 m equal to m exponential. We know that t is 152. Therefore, we can cancel out here by multiplying the ln. So 152 k equal to ln 2. So negative ln 2. So 152 k equal to ln 2. Therefore, we can solve this one. K we can get here. Alright, with 3 significant figures. Okay, we consider this one, 3 significant figures, because 0, 0 here we not consider as figure. Okay, proceed to example 3. We assume that the population of the earth changes at a rate proportional to the current population. Write the differential equation satisfied by the population. Okay, population, we know that it is a rate of increase, right? So dp over dt, the population over time, equal to kp, the constant. And then we separate the variable p to left hand side. Okay, 1 over p dp over dt equal to k. We can bring dt to the right hand side. Integrate 1 over p, we have ln p equal to integrate k, we get kt plus c, the constant. So multiply both sides with exponential, we get p equal to exponential kt plus c. And then p equal to exponential kt plus also will be multiplication of exponential c. Therefore p equal to, we let this one is as a exponential k t. Then B, in 1990, the population is estimated to have been about 3.9 million and 2000 about 5.3 million. By solving the differential equation and fitting this data, estimate the population at time t. Okay, when t equal to 0, in year 1990, the population is 3.9 million, and then P, we have just now, the general equation is a exponential kt. So this one we substitute, we will get a exponential 0. So we let t equal to 0 in year 1990. Then you can get here a is 3.9 million. We can substitute into the equation. Okay, and then in 2000, year 2000, about 5.3 million. So from 1990 to 2000, the t is 10 years, right? Which is in 1990 we let as t equal to 0, and then to 2000 t is 10 years. The population is 5.3 million. Therefore here we get p is 3.9 million exponential kt. Okay, then we substitute the value of p. Okay, we have just now p is 3.9 million exponential kt. So what say, we substitute the value of this one into this equation. Can we solve this by multiplying? Here multiply, so bring to the left hand side, you can get 5.3 over 3.9, and then we can get the value of k 0.03007. So therefore p, the population p is 3.9x million, 3.9 million exponential 0.0307 t, the general form. And then here we look at the C, question C. Hence estimate the population in 2020. So from year 2000 to 2020 is 20. So start from 1990 to year 2020, the t is 30 years, right? We let 1990 is t equal to 0. We have the general form just now, okay, this one. So we substitute the value of t. We can estimate in 2020 is 9.79 million. Okay, so means that in year 1990 we can estimate the population in 2020 by using the differential equation. Okay, hence the population in 2020 is 9.79 million. In example 4, under certain condition, the rate of cooling of an object varies with the difference between the temperature at the object and room temperature. Okay, given that the temperature of the object at any time t is theta, the constant room temperature is theta naught. Write down a differential equation to describe the rate of cooling of the objective. So rate of cooling means that it will be decrease the temperature, right? So if it is decreased, means that it will be negative. So the given further from information that the room temperature is 20 degrees Celsius, find a general solution of this differential equation. Okay. d theta over dt, okay, the cooling is the decrease of the temperature, it will be negative. Okay, theta minus room temperature. Okay, theta is the temperature of the object. Okay, so theta naught is room temperature, so we must minus theta naught. Okay, given is the room temperature is 20 degree. Okay, we minus 20 degree. We separate the variable theta. Okay, bring to the left hand side. We get 1 over theta minus 20 d theta over dt equal to negative k. Okay, we integrate both sides. We will get here integrate 1 over theta minus 20. We will get ln theta minus 20. Integrate k, we will get negative kt plus c. Okay, multiply with exponent both sides. Theta minus 20, we will get exponential negative kt plus c. And then we know that the plus here is the multiplication. Then we can get theta is equal to a exponential negative kt plus 20. That is the general form. If it takes 12 minutes, okay. Now we look at the when t equal to 0 first. Okay. When t equal to 0, it is 100 degrees Celsius. Okay. Because question B, if it takes 12 minutes for the object to cool from 100 degrees Celsius to 50 degree. So therefore, when t equal to 0, it is 100 degrees Celsius. Okay. Given the information in the equation here, okay. To cool from 100 degree to 50 degree, it will take 12 minutes. So when t equal to 0, the at initial point. So t equal to 0 at initial point, it is 100 degrees Celsius. Okay. So just now we have the general form is a theta a exponential negative kt plus 20. Okay. We substitute the value of 100 degrees Celsius here. A t equal to 0, a exponential 0 plus 20. So therefore a equal to a 80. So we can put the substitute the value of a with 80. Okay. When t equal to 12, it is just now when t equal to 0, it is 100 degrees Celsius. So it takes 12 minutes to cool down from 100 to 50. Okay. So now T12, it is theta value is 50. Just now we have 80 exponential negative kt plus 20, right here. So we substitute the value of theta is 50. And then we solve this one. Right. We will bring out here, get 30. And then also we can bring out here to right hand side, multiply with ln and then we can get K value here. So now we have the value of K. And then the question, and then find the time taken for the object to cool from 50 degree to 25 degree. Okay, we don't know the value of T, right? So when theta 25, okay, we substitute into the equation, this one. Okay, we don't know the value of T. So therefore here, okay, we bring the right hand side to the right hand side. Okay, we can get 5 here, and then 80 over 80 bring to the right hand side, multiply with ln, okay, to neutralize the exponential, and then we get T is 33.92 minutes. So here, since we have the general form, right, we take the general form. So when 100 degrees Celsius to 25 degrees Celsius, it takes 33.92. But here the question asks, find the time taken for the object to cool from 50 degrees Celsius to 25. So since here is starting from 100 degree, so we need to minus the total time minus 12. Okay, to cool to take time to taken to cool down from 50 degree to 25 degree. So we get here 21.92 minutes. Okay, exercise here, you can make this one, you can do this one. Okay, we do it together. This exercise. A small steel ball bearing is dropped at rest into an oil tank. The velocity v centimeter per second after time t is s is given by the differential equation. So dv over dt equal to 5 times 2 minus v. Show that this equation v equal to 2 times 1 minus exponential negative 5t. So given dv over dt here given, okay, we separate the variable v, bring to the left hand side. So integrate dv equal over 2 minus v equal to integrate 5 dt. Okay, here we can get negative ln 2 minus v, okay, equal to 5t plus c, where c is a constant. Since the steel ball bearing is dropped at rest, means that v equal to 0. Okay, when t equal to 0. So negative ln 2 minus 0 equal to 5t just now, 5t plus c, we substitute t equal to 0. We get c equal to negative ln 2. So we substitute into this equation. And then here we can solve ln 2 minus v minus ln v equal to negative 5t. We multiply with the negative here. Then this is negative, this is a division. Can solve here v. You can say that v equal to 2 1 minus exponential negative 5t. So it is proven. So st just now v2, okay, st approach the infinity here, infinity, and then v approach to 2. Okay, here, so v approach to 2. It is horizontal asymptote. Okay, when v equal to 0, t equal to 0. Okay, we look at question C. Show that the distance traveled by the steel ball bearing after 3 seconds is about 3 over 5 meters. Okay. So since v is rate of change of the distance, right? So ds over dt. Okay, if we want to get the distance or displacement, we will get integrate v dt. So just now it is a v, so ds over dt. So it is given, okay. Integrate ds, we will get s, and then integrate this one, 2 times t minus minus, okay, plus exponential negative 5t over 5 plus c. Okay, with the grade, this one exponential negative 5t, we get itself over negative 5, right? So it is negative, so negative negative, it will be positive. And then please don't forget c. And then when t equal to 0, s equal to 0, we substitute into this equation. We can get the value for c is negative 2 over 5. So substitute, and then we get the general form. But when t equal to 3, we have this equation, the particular solution, okay, because we have the value of c, and then we substitute the value of t equal to 3, right, which is this is the approximate to 0. Then we can show that 3 over 5 meters. The distance traveled by the steel ball bearing after 3 seconds is about 3 over 5 meters. Okay, that's all for today. Thank you for watching and take care and stay safe. Bye bye. See you again.